what we're going to start doing at the moment is for the next few sessions is basically focusing on model-based methods, and this is the first part of model-based methods, and we'll focus on area-level models. And in a moment, I'm going to explain to you what this all means. It is important to say that this section is very well linked with the materials that Angela covered during the first almost 9 hours of the course. So you will see how the estimators, both the point estimators and also the variance estimators as we spoke about, will directly fit into the area level model that we're going to present. One thing I wanted to say is that we're going to see a snapshot of methods. So we're going to see a number of methods around area level models. It's inevitable that we will not be able to cover the entire of this literature, because effectively that's a vast literature, but hopefully that will give you a quite good starting point, basically, in terms of starting to think how these models can be used. Okay, so without further delay, I'm going to just recap what we already said. By now you should be very familiar with that. I hope my slides are moving through. So when we talk about domains, so we tend to talk about small area estimation. Effectively, a more generic term to use here is domain, and that domain can be. Can you hear me? Yeah, and that domain can be a subpopulation of the population of interest, and can be planned or unplanned. Okay, because sometimes you end up basically with cases where sample is not allocated to domains. Effectively, it's something that you cannot really do anything about. It's something that is not part of your sampling design, effectively. So we can have geographic areas, which we spoke about, but you may be interested in a combination of geographic areas and other socio-demographic groups. For example, in your monetary poverty, you are clearly interested in municipalities, but you might be also interested in poverty rates that are municipalities split down, disaggregated by some other characteristic. It may be an ethnicity characteristic, or it may be some gender characteristic, or some age characteristic, and so on. So that's effectively means that you can further segregate or disaggregate your domains by other domains that might be, by other characteristics that might be of interest in an application. Okay, so occasionally we'll talk about domain as opposed to just area, small area estimation. So obviously you've gone all of this through all this with Angela, so I don't have a lot to add here. So as Angela said, direct estimators may be unreliable, or may have large variances. It will depend on what the variable that you're trying to get estimates for is, and also it will depend on the sample sizes. Normally you will get large variances because you might have small sample sizes in the domains, but this is not the only reason, as we just discussed in the previous session. Synthetic estimators, it might be one way of trying to borrow strength from other data, are typically biased, as Angela explained, and so one way to try and get a synthetic estimator without using any auxiliary information is to assume that you have a larger domain, and the value for the larger domain holds also for the smaller domains with this within this larger domain. And then you have also composite estimators potentially, which normally are a combination of between the direct estimates, which are unbiased but may suffer from high variance, and the synthetic estimator, which is possibly biased but with lower variance. And you're trying to find an optimal combination in some sense, depending on a weight denoted here by gamma I. Okay, and Angela described the notation that I use here is slightly different, but we still use I for domain, indicating a domain, and theta for indicating the parameter of interest, the target parameter of interest. So the weights of that combination above will depend on some kind of the mean squared error estimator of the synthetic or the variance of the direct. But as Angela explained again, that can be a very difficult task, estimating the the weights, and can be quite a difficult task in this case. So let me start now talking a bit about model-based methods. So the framework is completely different here. You don't assume that the population is fixed, and then you repeatedly select samples from that fixed population. So you no longer assume that you have this kind of randomization process of selecting the samples, but effectively what you assume is you assume a statistical model. And of course, you have to make assumption about the process that generates the population variables of interest. So basically, we assume that the population, what you observe in the population, has been the outcome of some kind of stochastic process that can be described via a statistical model. And you have to make some assumptions about how that model looks like. So model-based methods overcome problems of design-based methods. Okay, you will see that it's a very good tool in terms of overcoming some of the problems that you have been going over with Angela in terms of description of the limitations that design-based estimators can have. And using models allows you to borrow strength from all the data across space, across time, and you can account also for multiple data sources and multiple sources of uncertainty. But there is a big but here, and that's why I say, however, the validity of the inference depends on having a well-specified models, and also you need to use tools for testing the model assumptions. So unlike the design-based inference, which is purely non-parametric in some ways, I mean, it doesn't depend on a model, it's purely based on selecting repeated samples from a fixed population under some sampling design, some strategy. Model-based methods depend on assumptions, and in many cases, assumptions are very strong. And as a result, the game that you have to play here is completely different. So you see there is nothing free effectively in this kind of process. On one hand, you have design-based estimators that are have very good properties and they are design unbiased and so on, but the problem is that they may suffer from lack of precision or accuracy when you go down to the domain level, to the small domain level, whereas with models you are able to possibly borrow the strength from all related data and improve accuracy and the accuracy and the precision of your estimates, but at the same time, the price you pay here is that you have to make assumptions that in many cases might be unverifiable, right? So you have to try and test whether these assumptions hold, and also have a lot of diagnostic tools to see how close, how good your estimates are, the estimates that are coming out of a model effectively, how good the model-based estimates are. Let's talk a bit about types of models and data requirements, because one of the things that is important to understand, and as we go through these sessions now, I think as in the previous session, I think it's a good time to start thinking how this links to the available data sources within DANE. So we're going to see in the next session a group of models called unit level models that are very popular models in the small area literature. In this case, what the models, the way that the methods based on unit level models work is that you use some kind of unit level data. The unit there can be the individual or the household, as it might be the case with your data. And this data come from some survey. So there is an assumption, a strong assumption, not a strong assumption, but an expectation that you have some ground truth data that comes that are collected via a proper probability sample. Okay, and you use this unit level data to estimate a model, whatever that model might be. Okay, and we will see examples of what this model looks like. And then what you do is you combine the model estimates with some population level covariates. In the simplest case, the type of population level covariates you need are area level population covariates. So that may be coming from some census, if you have the census data, or if you use administrative data representative of your population. Again, you can use some of these population covariates. And the population covariates are effectively relevant to what you're modeling. So effectively, if you try to set up a model for income that you can then use for poverty mapping, then the covariates that you use to estimate the model should be predictive, obviously, of what you're trying to model. So the setup that I describe here with unit level models, the data setup, works well for estimating small area averages, for example, using a linear model. Okay, so when the interest is basically on estimating, for example, the mean income in the different municipalities, so having access to area level population covariates is absolutely fine. Okay. If you are interested in estimating other parameters that are more complex, more general parameters, for example, it may be things like a poverty gap or a headcount ratio or a Gini coefficient or a quintile Shor ratio, these are examples of things that are maybe estimated as part of a poverty assessment exercise, then the access, then you require more detailed data. So if you want to use unit level models to do some poverty mapping exercise, in most cases, the assumption is that you will have access to population level microdata. So that means that you will see that some of the popular methods that are used for poverty mapping require the access to census microdata. In your case, it may be census microdata, or it may be microdata from administrative sources or some kind of other data. Okay, so because you work within a national statistical office, the issues with data access that external people may face, you may not have this issue. So I'm expecting that you will have access to the data for poverty assessment. But generally speaking, when considering unit level models, and when considering unit level models in order to estimate more complex parameters than kind of linear statistics, for example, small area means, then or averages, then the data issue, accessing the data, the level of data set that is assumed by some of these methods that we will come across later in this training is problematic. The second aspect I want to mention here is effectively, until now or in recent applications, a lot of the methods assumed some access to census data. And in some countries, or in a number of countries, census data are not very frequent in terms of happening, because it's an expensive exercise running a census. And as a result, what you end up doing in some cases is effectively building a model using the most recent census data. And then what happens is, as you move away from the census time, then there are problems that you start basically facing. Okay, so there is a big movement effectively to use population level data that are as frequently updated as possible. Okay, so that's why a lot of people now have interest in applications in terms of using geospatial data and other forms of data. For example, administrative data might be a good example where population level data might be updated on a more frequent basis. This is about unit level models that we will see in the next session. In this session, we're going to use area level models. And with area level models we use only area level data for model fit and estimation. So you don't need anything at unit level. You assume that everything has been aggregated up to the level of the area or the domain. For example, the area, in your case, the area, assuming it's municipality, then everything has been aggregated up to the level of municipality. Okay, so the model will be specified at the area level. The data access is, of course, less complex than access to unit level data. And one advantage is, as we will see, is that the accounting for a complex sampling design is a bit more straightforward, because effectively what we will be modeling there is estimates of direct estimates of what you're trying to measure. But there are other issues there, and as we go through the area level model, the basic area level model that I'm going to present, you will see that there are other assumptions that we have to make in order to allow this model to be estimated. And these assumptions sometimes are quite strong assumptions. Okay. So I will give you the main tool we're going to use in modeling modeling tool for both for area level models and unit level models is random effects models. I don't know how many of you are familiar with random effects. I know that some of you are economists, and random effects may not be something that you use. But can you help me to tell me if you have come across random effects models in your work before? Anyone?
I have heard of fixed effects and random effects models in economics. Mm-hmm. So in regression, but I don't know if this is the same concept.
It is the same, Jose. Yes. So it's exactly the same. But I'm going to give a very brief introduction, because what we will assume here is that this is the type of model that we're going to use in our model-based method. So small area estimation relies a lot on the use of random effects models. Okay, it's not the only type of model you can use. There are other types of models, but this is the main workhorse in terms of modeling strategy in small area estimation. And random effects models are providing a key way of modeling clustered data. Okay, now what do we mean by clustered data here? Clustering can be induced, for example, by a complex survey design. For example, because you have a multi-stage design, you end up basically, or a clustered design, you end up basically with observations that are clustered. And we know that observations that are clustered, for example, within areas, within groups, may be more similar than observations that are in different groups. Okay, so the fact that you are using a complex design to collect your data may create effectively something that where units cannot be assumed to be independent, but you have to account for the similarity in the observations in groups of observations that belong to the same group. Or it may be that you have natural structures. For example, units are clustered naturally within areas. You may have pupils nested within going to the same classroom and attending the same school and so on. So basically, random effects models are a way to capture the clustering that you have in data. And in your case, the simplest way of describing the clustering is that you have basically households, and the households are grouped within municipalities. Okay, and there may be an expectation that households that belong to the same municipality are more similar than households that belong in different municipalities. So one way to model this kind of data is by effectively using random effects models. Okay, so the key concept here, as we will see, is to include a random effect, which is area specific. In your case, it will be municipality specific. Okay, to try and account for what we call between area variability that is unexplained variability between the small areas, between your municipalities. Okay, so basically you will see that the random effects model is just a regression model that conditions on certain explanatory variables that hopefully are predictive of your outcome. And then you have an area effect to try and capture what remains unexplained after conditioning on X's, after conditioning on your explanatory variables. Okay, so let's see how it looks like. That's a linear model, what we call a linear mixed effects or random effects model. And here we're going to denote by I the domain or the small area, and by J we denote a unit. I think Angela in her slides used a K instead of J. Angela, correct me if I'm wrong, but effectively is exactly the same. So what we're saying here is effectively that you are modeling your Y, think of income here, and I'm using two subscripts, I and J. So we have J household in I municipality, and we're going to model that as a function of a set of explanatory variables X. So think of income, and X can be a set of predictor variables that are predictive of income. You can think of for example, education, level of education, employment of the head of the household. You can think about in some countries when they build some models for poverty mapping, they include a lot of household characteristics in terms of the facilities that the household has and so on. So basically, these are the X's. Hopefully, the X's predict Y quite well. And then you include a term called UI, and UI is effectively what we call a random effect. And that random effect will play a key role in model-based estimation. Okay, and then you have the usual unit level error term, which we call we denote by EIJ. Okay, so here we assume that we have within each we have M total areas. Okay, and then within each area we have N subscript I in households, for example. Okay, that's the two-level structure. And in the simplest case, you have to make some assumptions about the distributions of the random effects and about the distribution of the error terms here. And in the simplest case, you assume that these are normally distributed. The random effects are normally distributed with some mean 0 and some variance denoted by sigma squared u. And the error term is distributed by as normally with mean 0 and variance sigma squared e. Okay, and what you need to estimate as part of your model fitting process is you fit the model and you get the estimates of the regression parameters beta and also of the two variance components, sigma squared u and sigma squared t. And the other thing that is very important for small area estimation is that you also need to predict u. Okay, so the random effect for each of the areas. So, and you can do that using different methods. You can use maximum likelihood, you can use residual maximum likelihood, or other methods. And there is a lot of literature out there as to how to fit these models and obtain these parameter estimates. Right, so let's look now into the area level model. So what I'm going to do is I'm going to introduce the area level model for the next 10 minutes or so, or 15 minutes, and then I'm going to take a break, stop there, and then we're going to start again on Monday. Okay. So the Fay-Hayden model is one of the oldest models that have been used in small area estimation. So I have the reference here at the bottom is it was proposed by Fay and Hayden in 1979. So that's quite a seminal paper, and I think it's good to go through the paper and see how the model is defined. But I'm going to define it now for you. So first of all, I'm going to use an abbreviation here. I'm going to abbreviate the Fay-Hayden model as FH, so wherever you see this abbreviation, we are going to talk about the Fay-Hayden model. And that model comprises two parts. The first part is what we call the sampling model. And the sampling model effectively says that the direct estimates, you see why the direct estimates that Angela was talking about. So the direct estimate for area I, so theta hat I direct, is equal to the true parameter theta I in that area plus an error term EI. Okay, so the theta I here denotes the true area parameter. So think of mean income as your target parameter. Theta hat I direct is a direct designer-biased estimator. For example, one of the estimators that Angela presented, like the Horvitz-Thompson or the High-Brewer estimator. And EI is the sampling error of the direct estimator. Okay, so what you say is what I estimate from my sample using a direct estimator is equal to the truth plus an error term. Okay, and the error term basically is a sampling error of the direct estimator. And Angela just at the end of the last session gave you different ways to estimate both the direct estimates, but the point estimates, but also the sampling errors. So you can estimate the variance of the direct estimates, and that will give you a handle on that sampling error. On top of that, there is something else called the linking model. Okay, so what the linking model tells you is that the true area parameter theta I is related to a set of covariates xi via this model. Okay, so you say that my theta I is equal to xi beta plus an other term ui. Okay, beta is a set of regression coefficients like in any simple linear regression model, and ui is effectively the random effect. Right, so the xi here, you can see that the xi is a vector of area covariates, and the ui assumes is distributed according to some distribution that has not been specified here, right? So with mean zero and variance sigma squared u, and ei again follows a distribution with mean zero and variance sigma squared ei. So I haven't specified that these are normal distributions. That will become relevant when you come to estimate this variance component, the variance component sigma squared u, but it's not specified yet. Okay, so effectively, the Fay-Harriot model comprises two parts. You say, I know that my direct test, this is sampling part, I know that my direct estimates are equal to the true value plus a sampling error. So the direct estimates are distributed around the sampling, around the true parameter, and that distribution has a sampling error. And then you say that the true parameter is related to a set of covariates, xi, via this model that's specified as part of the linking model. Now, that leads us to something called the combined models. If I put things together now, if I put my sampling model and my linking model together, okay, so what I do is I take my linking model and I put it back into my sampling model. You see that this will define a combined model that tells that the direct estimates, theta hat I direct, are equal to, under the model will be xi beta plus ui plus ei, okay? Okay, so here is one of the important things about area level models. Now, you have two components here that need to be estimated, sigma squared u and sigma squared ei. Okay, sigma squared u is the variance of the random effects. Sigma squared ei is the sampling variance of the direct estimates. Because you're fitting a model at the area level, because you're trying to estimate a model at the area level, you only have one observation per area, and that's important to understand. What you have is one observation per area. So you have one direct estimate for each of the areas, okay? And then you have a set of covariates that are also at the area level, okay? You don't have unit level data, and that means that you cannot really estimate both variance components. You cannot estimate both sigma squared u and sigma squared ei here. So what you need to do here is you assume under this model, in the simplest case, that the sigma squared ei's are known. So you have estimates of the sampling variance because you know by now how to estimate the variances of the direct estimates. And basically you assume that the variances of the direct estimates are known. Okay, you don't consider them as unknown. So the only unknown parameters that you need to estimate are basically sigma squared u, you're between the variance of the random effects, and also the regression parameters beta. So that's a key part of that model, and it's good to understand. So we'll see in practice how this is done, and this will become a bit clearer also when Angela does gives you the first computer lab, because there you will see how the sampling variances are estimated using some standard software. But effectively, what you need in order to set up the model, you need to have area level data. So you need to have estimates of the direct estimates of the parameter of interest. That's the first thing. You need to have a set of covariates xi at the area level, and you need to have also the estimated sampling variances of your direct estimates. So you see that what you did in session 1 is the basic setup that you need, the basic data setup that you need in order to be able to do something with the area level model, basically estimate the area level model. So that leads us to something that then is very important for small area estimation. So that leads us effectively to the first thing we're going to see, which is called the best linear unbiased predictor, which we're going to abbreviate here by BLUP. Okay, so if I assume for now, and that's not the case, but if I assume for now that also my sigma squared u is known, okay, then my theory tells me that the best linear unbiased predictor under that model, which I'm going to now define as theta hat I BLUP, okay, is going to be a combination between the direct estimate and the synthetic estimate, okay, with some weights gamma I and 1 minus gamma I. So this very much has the form of the composite estimator that Angela presented in the last session, okay, but this is derived under this model, assuming that sigma squared u is also known. And that will depend, as I said, on an important factor called gamma I. And the question is, what is this gamma I? How is this gamma I decided? Okay, so as I said, the BLUP has the form of a composite estimator. The weights gamma I will depend, as you will see in a moment, on both variance components, both on sigma squared u and also on the sampling variance. Gamma I, you may come across in the literature, it's called the shrinkage factor, depending on whether you give a higher weight to the direct or you give a higher weight to this part of the estimator, okay? And sigma squared EI is the variance of the direct, and that depends on one key component of that is the sample size in the area, okay? So that's the form of the BLUP, of the best linear unbiased predictor. And so I'm rewriting this here, and just to get an intuition about what the BLUP does, think about it. If you have a very reliable direct estimate, right? So for example, say that you have a very big sample size in areas in Bogota, okay? Your direct estimate is very reliable. So the gamma I will be higher for the direct and less for the other part, okay? So the gamma I tends to give high, will depend how the gamma I is going to play out will depend effectively on how reliable your direct estimates are, okay? So if you want to write that in the form of a linear mixed model, so this estimator here can be written as, this predictor here can be written as in the form of a linear mixed model. If you do a bit of algebra, you will see that theta I BLUP can be written as xi beta hat plus gamma I times the difference between the direct estimate and the xi beta hat under the model. And that effectively, this second part here is a random effect, is a predicted random effect, okay? So you can write the BLUP in the form of a linear mixed model as xi beta hat plus ui hat, okay? And the gamma I is equal to sigma squared u divided by sigma squared u plus sigma squared ei, right? So think of a case where your sigma squared ei is very small. What does it mean? If my sigma squared ei is very small, that means that my direct estimate is very reliable, okay? And that quantity here will go close to 1, okay? Not quite 1, but will move closer to 1. So that means that I will be giving a higher weight to the direct and a lower weight to the rest, to the second part of the estimator. Whereas if the sigma squared EI is very high, then you say, well, actually, my direct estimates are not very reliable, so I'm not going to rely a lot on the direct estimates, and I'm going to move more into using this second part. Okay, so effectively, you're trying to find a best combination between the direct estimate and the second part that depends on the beta hats on the fit of the regression model. Okay, so this is how the model looks like. I'm conscious of time, so I probably, let me see. Yeah, I'm going to finish with this slide as a final slide. So let's look a bit at the mean squared error of the BLAP, of the best linear unbiased predictor. Okay, so the mean squared error of the BLAP is equal to the variance of the BLAP, because under the model, the expectation of that expression here of the theta hat I BLAP minus theta I, the true parameter, is equal to 0. Okay, so if you look at the variance of the BLAP, the variance of the BLAP depends on two things. It will depend on the sampling variance times gamma I. Okay, so if you go back here, you take this expression here and you apply the variance, effectively you will end up with gamma I times sigma squared EI, which is the sampling variance, and 1 minus gamma I squared times this expression here. And you see that this expression here depends on the variance of the regression parameter. So you see there are two sources now that contribute to the variance. One is the sampling variance of the direct plus the variance of the estimated regression parameters under the model. And we're going to denote that by these two components by G1I plus G2I. Okay. For example, if you have a large number of areas, okay, then the second component, G2I, will be quite small, and G1 will be what basically will drive the variance of the BLAP. Okay. However, the first part is equal to gamma I times sigma squared EI. Okay. And because gamma I is between 0 and 1, right, that will be less than sigma squared EI. Okay. So you see that effectively under the model, you're getting a bit of reduction because of this expression here. So with the direct estimate, you have the sampling variance in sigma squared EI, whereas the G1 term is equal to gamma I times sigma squared EI. Okay, so you will get, if you have very good covariate information, for example, and your sigma squared U is small because you have managed to explain all the between area variability, then you will get a lot of gains in this case. And that effectively illustrates the superiority of using a model over the direct estimator. So the game here with these models is to try and include as much covariate information, XI, that is predictive of what you're trying to predict, to try and reduce what remains unexplained between the areas. And we will come back to that on a number of occasions to try and illustrate that. So I want to recap here because I know that this is probably quite new to many people. Okay, so what I'm working with here is area level models. Area level models have a very particular setup, data setup, that we're going to see in practice. You need, the first thing you need is the direct estimates for each municipality, for each domain of interest. You need to have auxiliary information that is predictive of the direct estimates, and that's again at the area level or the municipality level in your case. And you also need the variances of the direct estimates, which are estimated using methods that were presented by Angela in the first part of the session. Once you have this set up, then you are ready to go. Okay, so you're ready to estimate the Fay-Harriott model. The Fay-Harriott model has this form. You see on the left-hand side, you have the direct estimates. You don't have the actual values of the income as you would do in a regression model, but you have the estimates of the average income for the municipalities, and you relate these estimates to a set of covariates, and you include also a random effect for the area. Okay, under that model, the first thing you do is, first of all, you assume that the sampling variances are known, and as you have estimated them as part of your direct estimation. And to get the BLAP, you also for now assume that sigma squared U is known, and that will give you the form of the BLAP, okay, which, as I said, is a convex combination between the direct and the regression synthetic part under the Fay-Harriott model. So we covered that. We showed that the BLAP can be written in the form of a mixed model as xi beta hat plus ui hat. We explained how the shrinkage factor looks like. The shrinkage factor is nothing more than the ratio of the between group variance divided that between municipality variance divided by the between municipality variance plus the sampling variance, and effectively that tells you how this gamma I is going to work in terms of giving more weight or less weight to the different parts of the BLAP. And the final thing that we presented is the mean squared error of the BLAP. And remember that the BLAP assumes that sigma squared u is known. So you see that because we assume sigma squared u is known, that the variance of the BLAP will depend on the variance of the direct and also on the variance of the estimated regression coefficients. So what we're going to do on Monday, when we meet on Monday at 3 o'clock, is we're going now to go from BLAP to the empirical best linear unbiased predictor. We cannot assume that sigma squared u is known. We know that sigma squared u has to be estimated under the model, and effectively we're going to see what impact this will have in terms of the mean squared error of the BLAP. Okay, because that's really a key point in all the kind of model-based small area estimation that we will cover in this training. Okay, so I'm going to stop here, and I would like to ask you for now if you have any questions.
I want to ask. You mentioned that the dependent variable, for example, could be the average income for the domain level, but when or how we go from there to the poverty incidence, or the dependent variable could be also the poverty incidence directly.
It could be a direct estimate. So it could be a direct estimate of the proportion of people below the poverty line in a particular municipality, provided that your direct estimate is design unbiased. Okay, that's absolutely fine. So you can use we have an example a bit later, which includes an example of modeling directly the proportions of poor people in municipalities. Okay. One thing that you have to be careful when you model proportions is that perhaps the linear model may not hold. So in the example, because it goes between 0 and 1, so in the example that that we're going to give, we have an example of modeling proportions where you may have to use a transformation, a kind of transformation of the proportion. But yes, in answer to your question, if you want to translate that into operations within DANE, I think it's important to remember that you can get direct estimates of the proportion of poor people in municipalities. Okay, you have them at municipality level. That's your dependent variable effectively, and then you need to find a set of covariates again at the municipality level that will be predictive of that proportion of poor people. Okay, does this answer your question, Jose?
Perfect, thank you.
Okay, the other thing I wanted to say, for this session, we're going for the area level models, we're going to assume that we're modeling means or proportions or something that we know is unbiased, right? When you move to more complex statistics, okay, for example, someone might be interested in modeling a Gini coefficient, for example, okay? We know that estimators of that kind, parameters of that kind might be affected quite severely by bias, especially in small samples. So there is literature that allows you to use area level models with more complex parameters, but these require a bit of additional work in the sense that you may have to find some bias corrections before you set off to use an area level model. Okay. We are not going to cover area level models for this kind of parameters, but I'm going to give you at least one reference where they do that. I want you to be aware of that. But for this session, and what ideally I will be very happy to see you doing, is that if you can apply an area level model to something like the proportion of households below the poverty line in municipalities and set up an area level model for your data, that will be great, because then we can see how this area level model works. We can make use of the materials that Angela presented in the first part, i.e. estimating the obtaining the direct estimates of the proportion of poor people, obtaining the variance of those estimates, accounting for the complex sampling design potentially in Colombia, and then setting them up into an area level model, and then outputting the estimates, getting also mean squared errors under the Fay-Hayot model, and contrasting the area level estimates against the direct estimates, okay? And as we will see with the model, we will be able also to predict or to estimate for municipalities that are not part of the sample, okay? Obviously assuming that the model holds, because if the model that we train with the sample data does not hold for the non-sample data, and perhaps in the case of Colombia, there's a good reason for this model not to hold, because the reason that these areas have been excluded it's not random, there is a reason, because the cost of getting there and doing the surveys is very high, then the model will not help you a lot. So you cannot be certain about your inference, but at least you have a way to predict for out of sample municipalities, provided that the model you estimate with the sample municipalities holds also for what you don't observe. Okay, so this is something we're going to pick quite repeatedly as we go through this course. And by the way, don't worry too much about the theory at this stage, because we're going to do a lot of practical work with this model. I have already included some slides with outputs from the software and so on, so that will help you to understand a bit better how the model is set up. Okay, I'm going to stop here. Angela, I don't know if you want to come in and say something.
No, Nikos, actually, I have nothing else to add.
Okay.
At this stage.
Jose, Audrey, Paula, Angelica, are you okay to stop at this stage? Are you happy with what we have covered today? Shall we wrap up? Yeah. Okay, good. Okay. So one thing I want to remind you, keep translating the cases, the data cases and the models and the techniques and the estimators, you see that into the Colombian context. Okay, that's really important for us.